Tonight may be the pivotal moment when everything transforms. 3 Atlas, an entity originating from beyond our stellar neighborhood, is traversing the vicinity of our Sun, a passage astronomers are terming the ultimate assessment. Should it exhibit an increase in speed or demonstrate capabilities that transcend the Sun's gravitational influence, it would strongly imply external direction or control, thereby providing our initial confirmation of extraterrestrial ingenuity. Conversely, if its behavior is purely a natural phenomenon, the enigma will persist. However, if it is not, the vastness of the cosmos will suddenly feel considerably more confined. Remain engaged as we dissect every plausible outcome and its consequential ramifications. By the conclusion of this night, our entire comprehension of existence, time, and the very essence of humankind may undergo a profound revision. Section 1. The initial assertion and the reality check at perihelion. If 3 Atlas performs as anticipated tonight, the world will irrevocably change. As you absorb these words, an entity originating from outside our solar system is approaching the closest point in its solar orbit. This juncture is scientifically designated as perihelion. For this particular traveler, it signifies considerably more than a mere celestial marker. This could represent the instant humanity ascertains that we are not solitary beings in the universe. Alternatively, it might confirm our enduring apprehension that the cosmos remains as inscrutable and indifferent as ever. Regardless of the outcome, the events transpiring within the ensuing 72 to 240 hours will fundamentally redefine our perceived place within the universal structure. The entity in question is formally catalogued as C2025N1. Its discovery on the first day of July 2025 was credited to the Atlas Survey Telescope located in Chile. Scientific authorities have validated it as the third detected visitor from outside our solar system, leading to its informal appellation, 3 Atlas. Unlike celestial bodies formed within our solar system, this entity originated from an entirely different cosmic locale, bearing with it the frozen chemical compositions and, potentially, the hidden knowledge of another star system. Its trajectory offers definitive insights into its origins. The orbital path is hyperbolic, signifying it will not traverse our region again. It is moving through our celestial vicinity at velocities indicative of its extrasolar provenance. The measured excess velocity is approximately 60 kilometers per second, a speed far exceeding that attributable to any object gravitationally tethered to our Sun. This evening, October 29, 2025, 3 Atlas will reach perihelion at a separation of roughly 1.35 to 1.44 astronomical units from the Sun. This equates to approximately 203 to 210 million kilometers, positioning it between Earth's orbital path and that of Mars. From our terrestrial perspective, however, a vexing reality confronts us. The object is currently in solar conjunction, meaning it appears too proximate to the Sun in our sky for direct visual observation. We are precluded from observing it during these critical temporal intervals. The Sun's overwhelming luminosity renders any attempt to capture imagery or track the object in real time futile. Consequently, we must depend on alternative methods. These will be more nuanced and potentially more revealing. Indirect evidence will only become discernible in the hours and days that follow. What type of indirect evidence are we anticipating? Astronomers will be scrutinizing minute deviations in its course that cannot be attributed to gravitational forces alone, anomalous thermal emissions suggesting the release of active energy, unexpected outgassing patterns deviating from typical cometary behavior, or even the emergence of secondary entities into independent orbits. These would serve as indicators of deliberate construction, controlled operation, or intentional purpose. If 3 Atlas represents more than just a celestial vagrant from interstellar space, if it embodies technology or serves a specific function, then perihelion would be the opportune moment for action. This is the period of peak velocity, when the Sun's gravitational influence provides the maximum acceleration and when any applied propulsion would yield the most substantial alteration in trajectory with the least expenditure of energy. Engineers refer to this as the O'Neill effect, and if this object was engineered, its creators would possess an intimate understanding of how to leverage it. The gulf between public pronouncements and scientific consensus has never been wider. Media outlets have been disseminating speculative narratives for weeks, with some suggesting this could mark humanity's inaugural encounter with alien technology. Avi Loeb, the Harvard astrophysicist who famously posited its artificial nature, has contributed provocative commentary regarding unusual chemical signatures. Public advisories have proliferated online, with some alleging institutional concealment or asserting that governmental bodies possess undisclosed knowledge. Concurrently, professional astronomers advocate for restraint, reminding us that extraordinary assertions necessitate extraordinary substantiation and that we have previously been misled by natural phenomena. The space between these contrasting viewpoints, between unfettered conjecture and measured skepticism, is where the verifiable truth will ultimately emerge. Consider what was already established prior to this evening. Oumuamua, the first unequivocally identified interstellar object detected in 2017, ignited years of debate concerning its anomalous acceleration and elongated form. Borisov, the second interstellar visitor identified in 2019, behaved in a manner entirely consistent with a conventional comet, somewhat alleviating the prevailing tension, but also disappointing those who anticipated a more extraordinary revelation. Now we have 3 Atlas, and from its inception it has presented enigmas that defy conventional categorization. Its orbital path is remarkably aligned with the ecliptic plane, the flat expanse where planets orbit our Sun, a statistical improbability for a random interstellar traveler. Its composition exhibits anomalies that some researchers find challenging to explain through natural mechanisms alone. Its arrival, coinciding with an era when humanity possesses the technological capacity for detailed detection and analysis of such entities, feels almost orchestrated, though this perception may simply stem from the cognitive predisposition of a species yearning for celestial companionship. Over the next 72 to 240 hours, data will commence flowing from observatories across the globe and from spacecraft strategically positioned throughout the solar system. Astrometric measurements will precisely determine the object's position with millimeter accuracy, revealing any divergence from purely gravitational projections. Spectroscopic analyses will scrutinize the light reflected or emitted by the object, searching for chemical signatures indicative of artificial processes. Infrared telescopes will detect any extraneous heat that might signify active systems or propulsion mechanisms. Radio telescopes will listen for any electromagnetic transmissions, however faint, that could suggest intentional broadcasting. Each piece of incoming data will either fortify the case for a natural explanation or illuminate the possibility that we are witnessing something entirely unprecedented. The countdown has commenced. However, by the time these words reach you, perihelion may have already transpired. We stand at the precipice of revelation, suspended between the comforting assumption of a cosmos devoid of other sentient beings and the awe-inspiring, albeit daunting, prospect that we are being observed, studied, or at the very least, acknowledged by an intelligence that has traversed the interstellar void. What unfolds next hinges not only on the data obtained, but also on our interpretation, the controllers of the narrative, and humanity's readiness to confront the implications of contact, irrespective of its indirect nature or ancient origins. Section 2. Initial observations and the metrics of the acid test. The critical assessment of 3E Atlas hinges upon quantifiable data, specifically the parameters dictating its spatial movement. Astronomers will be meticulously examining what is known as delta V, which quantifies the alteration in velocity not attributable to gravitational forces. Every celestial body within our solar system adheres to a predictable trajectory dictated by the gravitational pull of the Sun and planets, a path calculable with exceptional precision. Should 3 Atlas deviate from these projected paths by even millimeters per second, sustained over days or weeks, it would present an anomaly demanding explanation. Natural comets do exhibit minor non-gravitational accelerations, originating from outgassing when solar radiation heats their icy surfaces, expelling vapor jets that function akin to miniature thrusters. The crucial question is whether any observed deviation aligns with this natural phenomenon or suggests an entirely different origin. A maneuver leveraging the O'Neill effect would manifest a distinct signature within the orbital data. This effect capitalizes on the principle that kinetic energy escalates with the square of velocity, meaning a modest thrust applied at peak velocity results in a disproportionately significant change in overall energy. Perihelion represents the point of maximum velocity for 3 Atlas relative to the Sun, rendering it the optimal juncture for any deliberate trajectory adjustment. If the object initiated an engine burn or released stored energy during this period, we would anticipate observing a deviation in its trajectory in the subsequent days, with the divergence progressively increasing as more data points are acquired. The magnitude of this effect is of paramount importance. A delta V of 1 millimeter per second would be exceedingly difficult to detect and could readily be mistaken for natural outgassing, whereas a delta V of 1 centimeter per second or more would necessitate considerable scrutiny and multiple independent confirmations before any assertion of artificial origins could be cautiously considered. Measuring such minute deviations demands exceptional precision in astrometry, the scientific discipline concerned with determining the positions and velocities of celestial objects. Terrestrial telescopes, under optimal conditions, can achieve positional accuracy of approximately 0.1 arc-second. At the distance of 3 Atlas, this translates to uncertainties in the hundreds of kilometers. While this may appear imprecise, the cumulative data gathered from tracking an object over successive nights, coupled with statistical analysis to align observations with a predicted orbit, can reveal velocity changes at the millimeter per second level. The frequency of observations is also a critical factor. More frequent measurements facilitate earlier anomaly detection, but also amplify the potential for systematic errors to infiltrate the analysis. The timing of observation windows is equally significant, as 3 Atlas must re-emerge from behind the Sun before we can resume tracking, and any delay in acquiring new data prolongs the period of uncertainty. Several instruments and tracking networks will be dedicated to observing these potential deviations. The Minor Planet Center orchestrates astrometric observations from telescopes worldwide, compiling positional measurements and calculating updated orbital solutions as new data becomes available. Individual observatories contribute their own measurements, which are subsequently cross-referenced against predictions to identify outliers or emerging trends. Spacecraft missions operating within the inner solar system may offer observations from alternative vantage points, providing parallax measurements that enhance positional accuracy. Some missions are equipped with instruments sensitive to thermal emissions or capable of imaging faint objects against the backdrop of stars. The fundamental principle is redundancy. If multiple independent sources detect the identical anomaly utilizing distinct instruments and methodologies, the confidence in that detection escalates significantly. Astronomers will be generating what are termed residual plots, graphical representations illustrating the discrepancies between observed positions and predicted positions based on a purely gravitational model. In an ideal scenario where our model accurately accounts for all forces acting upon the object, the residuals would exhibit random scatter around zero, reflecting only measurement noise. Conversely, if the residuals display a systematic trend, steadily increasing in a specific direction over time, it indicates a genuine physical effect not incorporated into the model. Visualize a graph where each point represents a night's observation, with the vertical axis indicating the degree to which the object's actual position deviates from the prediction. If these points begin to march consistently upward or downward, curving away from the zero line in a discernible pattern, you have evidence of an anomaly. The challenge lies in differentiating this signal from spurious alarms caused by modeling inaccuracies, unaccounted solar radiation pressure, or subtle errors within the reference star catalog used for position measurements. False positives represent a persistent risk in this analytical domain. Natural outgassing from a comet can induce accelerations that mimic artificial propulsion, particularly if the outgassing is asymmetrical or occurs in discrete bursts. Solar radiation pressure, the gentle force exerted by sunlight on any object with a substantial surface area relative to its mass, can also produce minor accelerations that require meticulous modeling and subtraction. Inaccuracies in our assumptions regarding the object's mass, shape, or reflectivity can propagate through calculations and generate deceptive anomalies. What distinguishes a genuine engineered signature from these natural phenomena? The answer resides in the specifics, the direction of acceleration relative to the Sun and the object's trajectory, the temporal sequencing of any observed changes, the presence or absence of associated phenomena such as dust plumes or thermal emissions, and the consistency of the effect across multiple independent observations. Consider the potential observation of a plume that does not conform to typical cometary tail characteristics. Conventional comet tails are broad and diffuse, propelled away from the Sun by solar radiation and the solar wind, often separating into distinct dust and ion components with differing geometries. An engineered plume originating from a thruster might be narrow and columnar, directed away from the Sun without regard for its position, exhibiting a brief duration before cleanly ceasing. If thermal imaging reveals a heated region that persists longer than expected based on ice sublimation physics, or appears in a location inconsistent with passive solar heating, this would warrant intense investigation. The infrared signature of an engine, even a diminutive one, differs from the thermal glow of sunlit ice in ways that spectroscopy could potentially discern. The time frame for accumulating this evidence spans multiple phases. The initial data will become available within hours of perihelion once the object emerges from solar conjunction sufficiently to be observable once more. These preliminary measurements will be rudimentary, constrained by the object's position and luminosity, but they will provide the first post-perihelion orbital solution. Daily astrometric updates will refine this solution over the ensuing week, progressively reducing uncertainty and indicating whether any anomaly is present. Spacecraft observations, if any are scheduled, will arrive according to their own timelines, dictated by mission operations and data downlink schedules. Some crucial measurements may not be accessible for days or even weeks, during which time speculation will likely proliferate and competing interpretations will gain traction within scientific communities and public media alike. What would trigger an alert status among astronomers? This depends on the magnitude and clarity of the detected anomaly. A minor deviation barely exceeding the noise floor might prompt private discussions and initiate supplementary observations, but no public pronouncements would be made until further data either confirms or refutes the signal. A substantial, unambiguous deviation accompanied by unusual spectroscopic or thermal signatures would likely precipitate rapid coordination through established networks, potentially leading to targeted observations by major facilities and informal communication within the astronomical community. Prior to any formal declaration, the delicate balance between justifiable caution and excessive secrecy will be tested in real time, with careers and reputations on the line depending on who makes what claim and when. Section 3. What we have already gathered: Catalog and Imagery. Before we can evaluate potential occurrences at perihelion, it is essential to comprehend our existing knowledge of 3 Atlas, derived from months of observations preceding this moment. The object is officially designated C-2025N1 within the system maintained by the Minor Planet Center, the International Clearinghouse for observations of comets, asteroids, and other minor celestial bodies. This designation indicates its discovery within the first half of July 2025, marking it as a relatively recent addition to the catalog. The astrometric arc, the duration over which the object has been observed and tracked, now extends across several months, providing a robust foundation for calculating its orbit and narrowing down uncertainties. These uncertainties, naturally, persist, particularly for an object following such an extreme hyperbolic trajectory, but they have diminished considerably as more data has been accumulated. The orbital parameters present a striking narrative. The eccentricity measures approximately 6.14, confirming that this is not a captured object from our solar system, but a genuine interstellar traveler. Objects gravitationally bound to the Sun exhibit eccentricities ranging from 0 to 1, with 0 representing a perfect circle and 1 denoting a parabola that just barely remains within the gravitational sphere. Any value exceeding 1 indicates complete escape. An eccentricity of 6.14 signifies a dramatically hyperbolic trajectory with an immense excess velocity. This excess velocity, the speed at which the object travels relative to the local galactic standard of rest, is approximately 60 kilometers per second. For context, Earth orbits the Sun at 30 kilometers per second, and escaping the solar system from Earth's orbit requires an additional 12 kilometers per second. This object arrived with sufficient momentum to traverse our solar system with extraordinary speed, slowing only marginally as it passed the Sun before accelerating back into interstellar space. The inclination of its orbit measures approximately 175 degrees, indicating it is moving in retrograde motion, opposite to the direction of planetary revolution around the Sun. While this alone is not particularly unusual for interstellar objects, given their arrival from random galactic directions without a preference for our orbital plane, what is noteworthy and has drawn the attention of researchers is the close alignment of its orbital plane with the ecliptic, the flat disk defining Earth's orbit and generally shared by the other planets. The inclination deviates by only about 5 degrees from perfect alignment, a statistically surprising characteristic for a random visitor. Most interstellar objects are expected to arrive from arbitrary directions, with inclinations distributed uniformly across all possible angles. The discovery of one that happens to lie almost precisely within our planetary plane suggests either an extraordinary coincidence or an unknown selection mechanism. Alternatively, as some have theorized, it might imply that the object's trajectory was deliberately engineered to facilitate observation of or interaction with the planets. The imagery we possess from pre-perihelion observations primarily originates from the Hubble Space Telescope, with lead astronomer David Jewett and his colleagues conducting the studies. Hubble's exceptional resolution and sensitivity enabled estimations of the object's nuclear size, albeit with considerable uncertainty due to the difficulty in distinguishing the solid nucleus from the surrounding dust coma. These observations suggest a nucleus radius ranging between 0.16 kilometers and 2.8 kilometers, a broad range reflecting the ambiguity inherent in the data. Other estimations, based on differing assumptions about albedo, the surface's reflectivity, have pushed this upper limit even higher. The brightness of the dust coma indicates moderate activity levels preceding perihelion, consistent with ice sublimation, but not dramatically exceeding that of other comets at comparable solar distances. On the surface, nothing in the basic photometry unequivocally screams artificiality. However, one particular measurement has generated significant discussion in recent weeks. Investigations into how light interacts with particles in the cometary atmosphere, specifically how it scatters off them, have yielded observations described by researchers as exceptionally strong negative polarization at particular incidence angles. These polarization measurements are highly sensitive to the physical attributes of the dust particles, including their size, form, and makeup, with each material exhibiting a distinct polarization pattern. The majority of comets within our solar system display a typical polarization signature that reflects the characteristics of silicate and carbonaceous dust common in nascent icy celestial bodies. However, Comet 3I Atlas presents a polarization curve that diverges from this standard behavior, most notably within the negative polarization range observed at minor incidence angles. The creators of a recent academic paper, disseminated on the RCV preprint server, acknowledged this deviation but refrained from asserting it as definitive proof of anything extraordinary, instead proposing it might be indicative of unusual dust properties or a composition not frequently encountered in solar system comets. Concurrently, some visual representations circulating within online communities purport to showcase distinctive features or structures in processed versions of telescopic imagery. These community-generated enhancements often involve significant manipulation of raw data, intensifying contrast and refining details. While this processing can sometimes bring genuine features to light, it also carries the risk of introducing artifacts or amplifying background noise into perceived structures. Without access to the original, unaltered data and a clear understanding of the processing methodology employed, it is impossible to ascertain the authenticity of these enhanced images. Professional astronomers have adopted a more cautious approach, releasing imagery that has undergone rigorous calibration and error analysis. These scientifically vetted images, however, tend to be more reserved and less visually striking than those disseminated on social media platforms. The inherent uncertainty regarding the nucleus's dimensions poses a practical obstacle to interpreting any observed anomalies. Should the nucleus be on the smaller end of the estimated range, closer to 0.16 kilometers, its mass would be comparatively low, meaning even minor outgassing or thermal effects could induce measurable accelerations. Conversely, if the nucleus is larger, approaching 2.8 kilometers or more, its mass would be substantially higher, necessitating significantly greater forces to produce any non-gravitational acceleration. This ambiguity directly contributes to the broad uncertainty envelope surrounding the object's predicted trajectory. While its path is reasonably well defined, the precise magnitude of any acceleration due to solar radiation pressure or outgassing is contingent upon parameters that have not been fully determined. This leaves a degree of latitude for minor deviations to be attributed to natural phenomena. Nevertheless, a sufficiently significant deviation would become unmistakably apparent. The orbital prediction prior to the comet's closest approach to the Sun, known as perihelion, incorporated uncertainty bands accounting for both observational errors and modeling limitations. These bands have gradually narrowed as more observational data has been gathered, yet they have not disappeared entirely. The most stringent constraints originate from the most recent measurements obtained before solar conjunction rendered further observations impossible. Now, emerging from behind the Sun, Comet 3I Atlas will be reacquired by telescopes for renewed positional measurements. The critical question is whether its new position will fall within the projected uncertainty band or lie outside it, signaling that something unexpected may have occurred during the unobserved period around its perihelion passage. All of this contextual information is crucial because interpreting any potential anomaly necessitates a clear understanding of what constitutes normal and anticipated behavior versus what would be genuinely surprising. If the data reveals a minor deviation consistent with known uncertainties, astronomers will likely adjust their models without significant fanfare. However, if the data exhibits a substantial and systematic deviation that cannot be plausibly explained by natural causes, then we would be entering uncharted territory, and the crucial test would have revealed something truly extraordinary. Part 4 delves into the potential for observations from spacecraft windows and the subsequent tactical follow-ups. Beyond ground-based observatories, several spacecraft missions currently operational throughout the solar system may have opportunities to observe Comet 3I Atlas in the days and weeks following its perihelion. These spacecraft were not originally positioned or designed with this specific object in mind. However, their orbital paths happen to place them in positions where they could potentially gather valuable data, provided that mission controllers elect to redirect attention and resources toward this unexpected target. Each mission faces inherent limitations, including power constraints, data storage capacities, communication schedules, competing scientific priorities, and operational risks associated with retargeting instruments towards an unplanned object. The decision of whether any of these missions will actually observe Comet 3I Atlas hinges on immediate judgments being made by mission operations teams who are tasked with balancing scientific opportunities against programmatic risks. The European Space Agency's JUICE, Jupiter Icy Moons Explorer, mission, currently en route to the Jupiter system, is following a complex trajectory that includes multiple gravitational assists from planets in the inner solar system. JUICE's potential observation window for Comet 3I Atlas could open in the days following perihelion, depending on the spacecraft's precise location and orientation. JUICE is equipped with a suite of instruments designed for the study of icy moons, but these instruments are also capable of being redirected to observe other celestial bodies. This includes cameras for optical imaging, spectrometers for analyzing reflected light, and potentially even radar instruments that could provide unique insights into the object's surface characteristics. The challenge lies in coordinating such observations with the spacecraft's power and thermal limitations, ensuring that pointing instruments at an unexpected target does not disrupt critical mission operations or jeopardize sensitive hardware. Another significant encounter window is anticipated around November 3, 2025, when Comet 3I Atlas will approach Venus at a distance of approximately 97 million kilometers. While this distance is far too great for Venus itself to be affected by the object, spacecraft orbiting Venus or monitoring the Venusian environment could potentially observe it, provided their instruments possess the necessary sensitivity and field of view. Venus orbiters typically concentrate on planetary science, studying the planet's atmosphere, surface, and magnetic field. However, their cameras and spectrometers can occasionally be retargeted for brief observations of passing celestial bodies. The geometric configuration of this encounter is also important for trajectory analysis. If Comet 3I Atlas released secondary objects or experienced a change in velocity at perihelion, these effects might become more apparent as the object passes near Venus and the cumulative deviation from its predicted orbit increases. Earth's closest approach to the comet will occur around December 19, 2025, at a distance of roughly 1.8 astronomical units, or approximately 270 million kilometers. While this is not considered a close encounter in human terms, it represents the optimal geometry for ground-based observers in both the northern and southern hemispheres to acquire high-quality data using professional and amateur telescopes. Observations made in December will benefit from months of accumulated trajectory data, enabling very precise predictions of the object's location if only gravitational forces are at play. Any deviation from these predictions will be readily apparent by mid-December, assuming the anomaly is sufficiently significant to be genuine. This period also presents an opportunity for spectroscopic studies to refine our understanding of the object's composition, searching for chemical signatures that may have been missed or altered during the perihelion passage. The most distant, yet potentially most revealing encounter window is scheduled for March 16, 2026, when Comet 3I Atlas will pass within approximately 54 million kilometers of Jupiter. NASA's Juno mission, which has been orbiting Jupiter since 2016, could potentially direct its instruments toward the object, contingent upon favorable geometry and a mission controller's decision that it warrants the effort. Juno's cameras and spectrometers are primarily designed for studying Jupiter's atmosphere and magnetosphere, but they have demonstrated the capability to image other targets, including Jupiter's moons and distant asteroids. An observation of Comet 3I Atlas by Juno would provide a vastly different viewing perspective compared to Earth-based observations, potentially revealing features or behaviors that are invisible from our vantage point. For each of these potential mission observation windows, the type of data that could be collected is dependent on the capabilities of the instruments and the operational constraints of the spacecraft. Photometry, which involves measuring brightness over time, can reveal rotational rates, periods of heightened activity, or unexpected dimming events that might suggest fragmentation or the release of debris. Spectroscopic composition analysis examines the wavelengths of light to identify specific molecules or minerals based on their characteristic absorption or emission lines. Trajectory refinement benefits from any additional position measurements, particularly from spacecraft located far from Earth, as the parallax effect provides orthogonal constraints on the orbit. Radio monitoring, if any spacecraft is equipped with suitable receivers, could be employed to search for electromagnetic emissions at specific frequencies that might indicate technological activity. Although the probability of detecting such emissions is exceedingly low unless the object is actively transmitting, the constraints imposed by observational possibilities are real and numerous. Communication latency between Earth and distant spacecraft means that any decision to redirect instruments must be made well in advance, often days or even weeks before the actual observation window. Pointing restrictions are in place to safeguard sensitive instruments from direct sunlight or to maintain thermal stability. Data downlink schedules are typically planned months ahead, and the insertion of unscheduled observations can lead to delays in other scientific activities, creating friction within mission teams and with the broader scientific community that relies on the mission's data. Mission operations teams must carefully weigh the probability that Comet 3I Atlas is genuinely anomalous against the certain cost of diverting resources from planned scientific endeavors. The timeline for these potential observations extends over several months, unfolding a narrative arc that progresses slowly but inexorably. Perihelion occurs tonight, initiating a cascade of events. Days 1 through 7 following perihelion will see the first post-conjunction observations from ground-based telescopes, establishing whether the object remains on its predicted path or has deviated. Mid-November will bring the Venus flyby geometry and the possibility of spacecraft observations, should any have been scheduled. December marks Earth's closest approach and represents the peak season for both amateur and professional follow-up observations. March of 2026 offers the Jupiter window and a final opportunity for spacecraft observations before the object recedes beyond practical observational reach. Beyond this point, months and years of astrometric monitoring will continue, further refining the trajectory and searching for long-term deviations that may only become apparent over extended observation baselines. Risk factors introduce complications at every stage of this observational campaign. Ephemeris drift, the gradual accumulation of error in predicted positions, can occur if our models fail to account for all relevant forces. Space weather events, particularly solar storms that disrupt Earth's ionosphere or interfere with spacecraft operations, can lead to delays or degraded observational quality. Scheduling conflicts arise when multiple high-priority targets compete for the same telescope time or spacecraft resources. Mission priorities may shift in response to unexpected discoveries elsewhere in the solar system, potentially leading to Comet 3I Atlas being moved down the observation queue. Part 5 addresses immediate scenarios and a newsroom checklist. The upcoming 72 to 240 hours will compel us to confront one of three broad scenarios, each with distinct implications and requiring a different response from both the scientific community and the public. Understanding these scenarios in advance will help us to accurately interpret the data as it becomes available and to formulate appropriate, rather than reactive, responses. These three scenarios represent varying degrees of anomaly, ranging from entirely natural phenomena to potentially extraordinary circumstances, with a significant degree of ambiguity residing in the uncomfortable middle ground where evidence is suggestive but not conclusive. Scenario A represents the natural or control case wherein Comet 3I Atlas behaves precisely as expected for an interstellar comet traversing its perihelion. This scenario encompasses potential fragmentation events, increased outgassing activity as volatile ices sublimate under intense solar radiation, and minor non-gravitational accelerations consistent with cometary jetting. The trajectory would exhibit slight deviations from purely gravitational predictions, but these deviations would align with models of cometary outgassing in both magnitude and direction. No unusual thermal signatures would appear beyond those attributable to passive solar heating. No secondary objects would be released into independent orbits. Spectroscopic observations would reveal a composition that, while potentially distinct from typical solar system comets, could be explained by plausible astrophysical processes occurring in the object's birth environment around another star. In this scenario, Comet 3I Atlas would join the small but expanding catalog of interstellar visitors, each offering insights into the diversity of planetary systems and the mechanisms that eject debris across the galaxy, but none compelling us to consider the possibility of alien technology. Scenario B represents the opposite extreme. A clear, unambiguous, and engineered signature that cannot be accounted for by any known natural process. This scenario might include a detectable velocity anomaly large enough to preclude cometary outgassing or a trajectory deviation inconsistent with solar radiation pressure or natural jet activity. It could also involve the observation of a narrow, collimated plume during or shortly after perihelion, visible in infrared or optical wavelengths, and persisting for a duration that suggests active control rather than passive ice sublimation. Excess thermal emissions might be detected in locations or at intensities that cannot be reconciled with solar heating alone. Secondary objects could be released into trajectories that appear to be deliberately aimed at specific solar system destinations, such as Venus, Earth, or Jupiter. Spectroscopic analysis might reveal chemical signatures consistent with industrial processes rather than natural astrophysical chemistry, such as highly enriched metallic compounds or molecular species that require energy input for their formation. In this scenario, the probability of Comet 3I Atlas being an artificial object would rise from negligible to substantial, potentially necessitating a fundamental shift in our understanding of humanity's place in the universe. Scenario C occupies a precarious middle ground, presenting an ambiguous or borderline result that indicates something unexpected but not conclusive. For instance, the trajectory might deviate by an amount exceeding the expected range of cometary outgassing, but not sufficiently to entirely rule out a rare or extreme natural event. Thermal emissions might show a slight excess that could be explained either by unusual surface properties or by low-level active systems. Secondary objects might be observed, but their trajectories could be consistent with normal fragmentation rather than intentional targeting. Spectroscopic data might reveal chemical abundances that are unusual but not impossible through natural processes. In this scenario, astronomers would likely engage in passionate debates regarding interpretation, with some favoring exotic natural explanations and others arguing that artificial origins cannot be dismissed. Weeks and months would pass as more data accumulates, alternative models are tested, and the scientific community strives to reach a consensus. This scenario would test institutional integrity, as the pressure to announce exciting findings would contend with the professional obligation to maintain scientific conservatism until the evidence is overwhelming. Should scenario B occur, and an engineered signature be genuinely detected, the initial response within the first 24 to 72 hours would be rapid and coordinated, yet also chaotic and marked by uncertainty. Scientists detecting the anomaly would immediately scrutinize their data for errors, rerun their analyses with different assumptions, and contact colleagues for independent confirmation. If multiple groups detect the same anomaly using different instruments and methodologies, confidence in the signal's authenticity would grow. At that juncture, institutional stakeholders would need to be notified, including the International Asteroid Warning Network, NASA's Planetary Defense Coordination Office, ESA's Space Situational Awareness Program, and potentially even SETI organizations or astrobiology centers, depending on the nature of the detected signature. The question of who issues the first public alert would depend on institutional protocols and the individuals involved, but typically the Minor Planet Center or a major observatory might release a circular describing the anomaly without immediately claiming it as evidence of technology. Media attention would erupt regardless of the announcement's careful wording, forcing scientists into a reactive mode as they attempt to explain complex uncertainties to journalists and the public. If Scenario A occurs and Comet 3I Atlas behaves naturally, the narrative would shift towards understanding what can be learned from this particular visitor. Astronomers would classify it as an interstellar comet with unusual but explicable properties, and the scientific community would commence preparing papers detailing its composition, activity levels, and the insights these provide into planetary systems around other stars. Proposals for follow-up missions might emerge, suggesting that humanity should develop rapid-response spacecraft capable of intercepting future interstellar visitors for close-up study. The public might experience disappointment at the lack of an alien technology discovery, but the scientific value would remain substantial, as every interstellar object offers a window into environments inaccessible to direct observation. Scenario C, the ambiguous case, presents the most significant communication challenge. How can genuine uncertainty be conveyed to a public that demands clear-cut answers? How can transparency be maintained without fueling conspiracy theories about cover-ups or institutional bias? The solution would necessitate careful framing, meticulously explaining precisely what the data reveals, what alternative explanations exist, what additional observations are required to differentiate between them, and the projected timeline for reaching a definitive conclusion. Lower third graphics in video presentations might display labels such as preliminary data or multiple interpretations under review to indicate that conclusions remain tentative. Scientists must resist the pressure to overstate the significance of ambiguous results while simultaneously avoiding excessive conservatism that might dismiss potentially important anomalies as mere noise. A newsroom checklist for covering this developing story over the coming weeks would encompass several key elements. Firstly, identifying the critical data streams: astrometric residuals from the Minor Planet Center, spectroscopic results from major observatories, spacecraft observation reports if they materialize, and thermal imaging data from infrared telescopes. Secondly, establishing relationships with institutional stakeholders capable of providing authoritative information, such as NASA's Planetary Defense Office, ESA's Space Awareness Coordinators, SETI Institute researchers, and academic groups at institutions possessing relevant expertise. Thirdly, developing messaging frameworks that strike a balance between excitement and caution, avoiding hype that exaggerates the evidence while also refraining from dismissing genuinely anomalous results as commonplace. Fourthly, preparing for a protracted investigation, recognizing that definitive conclusions may take months or even years to emerge as accumulated data gradually narrows the range of possibilities. Consider a specific rapid response scenario. If astrometric data reveals a velocity anomaly exceeding 5 millimeters per second in a direction inconsistent with cometary outgassing models, and if that anomaly is confirmed by 3 independent observatories within 48 hours of its detection, what would be the ensuing course of action? The Search for Extraterrestrial Intelligence initiative may prompt subsequent radio telescope observations aimed at detecting electromagnetic signals that could indicate technological activity. NASA or the European Space Agency might assemble an urgent committee to evaluate if existing spacecraft can be rerouted for closer examination. The International Astronomical Union could issue a special bulletin to inform the global community about the anomaly and request further observations. Concurrently, the media frenzy would commence with journalists seeking interviews, social media platforms fueling speculation, and public demand increasing for official pronouncements. Managing this scenario necessitates collaboration among scientific bodies, clear communication frameworks, and a mutual understanding that exceptional assertions demand exceptionally rigorous scrutiny before being accepted as truth. Part 6 delves into chemistry and unusual phenomena, exploring composition, anomalies, and their implications. The chemical makeup of 3I Atlas has perplexed researchers since the initial spectroscopic data arrived months ago. We will now investigate what these chemical signatures reveal, what they conceal, and why some scientists find them challenging to reconcile with purely natural astrophysical processes. Chemistry functions as a unique identifier for the environment in which an object originated, containing information about temperature, pressure, radiation levels, and the elemental constituents present in its protoplanetary disk billions of years ago. By analyzing the light reflected or emitted by 3EI Atlas, we are essentially deciphering this identifier and attempting to match it with our knowledge of comets formed within our solar system and what might be anticipated from other stellar environments. The most comprehensive spectroscopic analysis was derived from observations utilizing the X-shooter instrument aboard the Very Large Telescope in Chile, detailed in a recent publication in the journal Astronomy and Astrophysics. These observations uncovered atypical spectral lines that do not precisely align with the conventional cometary profile. Standard comets emit light at specific wavelengths corresponding to common molecules such as water vapor, carbon monoxide, carbon dioxide, cyanogen, and various carbon-based radicals. 3 Atlas exhibits some of these expected characteristics, affirming its composition of ice and dust, as expected from any notable comet. However, it also displays anomalies in the relative proportions of certain compounds and in the behavior of these emissions as the object approached perihelion. The notably negative polarization measurement previously mentioned introduces an additional element of peculiarity, as polarization is indicative of dust grain properties. Negative polarization at minor phase angles typically necessitates specific combinations of particle size, shape, and refractive index not found in materials native to our solar system. Polarization studies operate by examining the manner in which light waves oscillate as they reflect off particles in the coma. Randomly scattered light becomes partially polarized, with the degree and orientation of this polarization contingent upon the scattering angle and the characteristics of the scattering medium. For the majority of comets, the polarization curve follows a predictable trajectory: slight negative polarization at very small phase angles, transitioning through zero, then exhibiting positive polarization that peaks before diminishing at larger phase angles. 3I Atlas deviates from this pattern, presenting a deeper negative polarization branch than anticipated. Some researchers interpret this as indicative of an unusual dust composition, possibly comprising grains with a higher metallic content or different porosity than typical cometary dust. Others posit that it might suggest an atypical particle size distribution with an overabundance of grains within a particular size range that enhances negative polarization through coherent backscattering effects. Pre-perihelion photometric behavior provides further insights into the object's nature. Dust production rates, as determined by analyzing the brightness and extent of the coma, demonstrated a power law dependency on heliocentric distance that subtly differs from typical cometary behavior. Most comets brighten as they approach the Sun, following well-established relationships that reflect the increase in sublimation rates with temperature. 3I Atlas followed a similar pattern, but with minor deviations in the power law index that some researchers found intriguing. These deviations could simply indicate unusual ice composition or an atypical distribution of volatiles beneath the surface, where different ices sublimate at varying temperatures and distances from the Sun. Alternatively, they might hint at something more unusual. However, linking photometric behavior to manufactured versus natural origins requires significant speculative leaps. Several competing hypotheses attempt to account for these chemical and physical anomalies within the established paradigms of natural astrophysics. The initial interpretation proposes that we are observing a genuinely rare or extreme cometary composition, reflecting conditions in its nascent environment around another star. Different stars possess distinct metallicities, meaning varying ratios of heavy elements to hydrogen in their protoplanetary disks, which comets subsequently inherit. A comet formed in a metal-rich disk might contain higher quantities of refractory materials or unusual mineral phases compared to comets within our solar system. The negative polarization anomaly could simply be a consequence of this compositional difference, revealing dust grains previously unencountered in our local sample of comets and asteroids. This interpretation does not require any exotic physics, merely the acknowledgement that the galaxy exhibits substantial diversity in planetary system compositions. A second interpretation invokes the thick disk origin hypothesis, suggesting that 3I Atlas might be a remnant from an earlier generation of stars that formed billions of years ago when the galaxy's chemical properties were different. The thick disk of the Milky Way hosts older stars with distinct kinematics and compositions compared to the thin disk where our Sun resides. Objects expelled from thick disk planetary systems could carry chemical signatures reflecting that ancient environment, potentially explaining unusual abundance patterns or dust characteristics. This perspective situates 3I Atlas within a historical context, designating it not merely as an interstellar visitor, but as a time capsule from an earlier epoch of galactic evolution. The third, and most contentious interpretation, posits the possibility of manufactured or artificially produced materials accounting for the observed signatures. This viewpoint remains highly speculative and is not substantiated by peer-reviewed research, yet it has gained traction in certain circles following public statements by Harvard astronomer Avi Loeb. Loeb has highlighted what he describes as unusual nickel emissions in the spectrum, suggesting the potential presence of industrial compounds or refined metals rather than naturally occurring astrophysical substances. Some media reports have mentioned nickel tetracarbonyl, a volatile organometallic compound utilized in industrial nickel refining processes on Earth. Although no peer-reviewed studies confirm the detection of this specific molecule in 3I Atlas, the claim remains unsubstantiated and warrants extreme skepticism until independent research groups replicate the observation and definitively rule out alternative explanations. Laboratory analogues are instrumental in our comprehension of how different compositions might manifest in spectroscopic and polarimetric observations. Terrestrial industrial processes that yield pure metallic compounds follow well-defined chemical pathways demanding specific conditions such as controlled atmospheres, precise temperatures, catalysts, and energy inputs. Natural astrophysical environments can produce metal-rich materials through processes like condensation in stellar outflows or high-temperature chemistry within protoplanetary disks. However, the resultant materials typically display a mixture of phases and oxidation states rather than the refined single-compound signatures characteristic of industrial manufacturing. If spectroscopic analysis were to genuinely reveal highly pure metallic emissions devoid of the expected oxidized forms or mixed phases, it would be difficult to explain through natural mechanisms and would legitimately raise questions about artificial origins. The Bayesian framework for evaluating these competing hypotheses requires us to consider both the probability of observing specific data points given each hypothesis and the a priori probability assigned to each hypothesis before data acquisition. If we begin with an exceedingly low prior probability for engineered origins, as is common among most scientists, then even moderately unusual chemical signatures do not significantly shift our posterior probability towards the artificial hypothesis unless those signatures are so extreme and specific that natural explanations become vanishingly improbable. This underscores why the burden of proof is exceptionally high for extraordinary claims. Our prior beliefs play a crucial role, and overcoming a very low prior necessitates overwhelmingly robust evidence, not merely suggestive anomalies. The question that persistently recurs is this: if one detects chemistry that deviates substantially from solar abundance patterns and from the range observed in solar system comets, at what point does that deviation constitute compelling evidence for non-natural origins? The answer hinges on the extent of our understanding of the diversity of potential natural environments. Our sample size of comets originating from other stellar systems remains minuscule, with only 3 confirmed objects, thus providing us with virtually no empirical basis for determining what is considered normal versus anomalous for interstellar visitors. Until we establish this statistical baseline through future detections, every unusual measurement could represent either a genuine anomaly pointing towards something extraordinary or simply a reminder of the universe's greater diversity than our limited local sample suggests. The enigma of its chemistry directly links to the propulsion question, as any engineered thrust system would likely leave chemical traces in its exhaust or waste heat. If 3I Atlas is more than an inert celestial body, if it possesses systems capable of altering its trajectory, then these systems must produce observable effects: expelled propellant, thermal emissions, electromagnetic signatures, or structural modifications. The chemical peculiarities observed thus far do not definitively point in either direction, but establish that this object is sufficiently unusual to warrant careful examination as we search for mechanical or energetic signatures in the post-perihelion data. Part 7 explores potential engineered propulsion architectures at 1.4 AU. Let us consider for a moment that 3I Atlas is not a passive interstellar iceberg, but rather an object that actively controls its trajectory in deliberate ways. What form of propulsion architecture would be feasible at perihelion distances of 1.35 to 1.4 astronomical units from the Sun? And what observational signatures would such a system generate? This question necessitates an examination of engineering constraints and possibilities not due to any confirmed evidence of artificial propulsion, but because understanding what to look for aids in its recognition if it appears in the data. The challenge is immense. Any propulsion system must function within the extreme environment near the Sun, generate sufficient thrust to effect a detectable trajectory alteration, and do so using energy and propellant mass that the object can carry or generate. High specific impulse chemical propulsion represents the most straightforward and familiar architecture, analogous to rocket engines used in human spaceflight. A chemical rocket combines fuel and oxidizer, releasing energy through combustion, and expels the hot exhaust at high velocity to produce thrust. Specific impulse, measured in seconds, quantifies engine efficiency, with higher values indicating greater thrust generated per kilogram of propellant. Chemical rockets typically achieve specific impulses ranging from 200 to 450 seconds, which is respectable for maneuvering spacecraft, but requires substantial propellant mass for significant velocity changes. If 3I Atlas were equipped with a chemical propulsion system and ignited it at perihelion, we would anticipate observing a narrow, directed plume of hot gas expelled in the direction opposite to the desired thrust vector. The exhaust would radiate heat in infrared wavelengths due to its high temperature, potentially creating a detectable thermal signature lasting for minutes to hours, depending on the duration of the burn. Astrometric measurements would reveal a sudden velocity change in the predicted direction, increasing over subsequent days as the object progresses along its modified trajectory. Pulsed thermal engines present a more unconventional option that harnesses solar energy rather than stored chemical energy. A solar thermal rocket employs mirrors or lenses to concentrate sunlight onto a heating chamber, elevating the temperature of a working fluid, which then expands through a nozzle to generate thrust. At 1.4 AU, solar intensity is diminished compared to Earth's orbit, but it remains substantial, around 500 watts per square meter. A sufficiently large collector area could gather megawatts of power, heating propellant to temperatures high enough for a useful specific impulse. The advantage of solar thermal propulsion lies in not needing to carry fuel, only propellant mass, and the potential to utilize any volatile material, even water ice or carbon dioxide sublimating from the object's own surface. The observable signature would encompass thermal emissions from the collector surface, directional outgassing as propellant expands through the nozzle, and trajectory changes consistent with the thrust vector. The challenge lies in constructing a system with adequate collector and thermal engineering to withstand concentrated sunlight without melting or degrading. Directed mass ejection via electromagnetic acceleration offers another speculative possibility. A mass driver or railgun utilizes electromagnetic forces to propel projectiles to high velocities, expelling them to generate thrust through conservation of momentum. Unlike chemical or thermal rockets that expel hot gas, a mass driver launches solid or liquid pellets at velocities potentially reaching kilometers per second. The specific impulse can be exceptionally high, meaning less propellant mass is needed for a given velocity change, but the system demands considerable electrical power for operation. At perihelion, solar panels could potentially supply this power, converting sunlight into electricity to drive the acceleration system. The observable signature would include the expelled mass itself, possibly visible as a stream of small particles trailing the object, and electromagnetic emissions associated with the acceleration pulses. Trajectory analysis would reveal velocity changes consistent with momentum transfer from the expelled mass. Beam-driven propulsion represents an even more speculative architecture, where external energy beams, such as lasers or particle beams, illuminate the object and impart momentum through radiation pressure or ablation. This scenario necessitates infrastructure located elsewhere in the solar system or in nearby interstellar space. A powerful transmitter capable of delivering megawatts or gigawatts of power across astronomical distances and maintaining precise targeting of a fast-moving object. The advantage is that the object itself would not need to carry fuel or power systems, only a surface capable of efficiently absorbing or reflecting the beam. The observable signature might include unexpected heating on one side of the object, asymmetric thermal emissions, or small but sustained accelerations in a consistent direction over extended periods. This architecture appears improbable given the immense distances and energies involved, but it is included for completeness, as ruling it out requires understanding what we should or should not observe. For each propulsion concept, we can estimate the required energy budget and compare it to what is physically plausible. Consider a delta V of 1 centimeter per second applied at perihelion to an object with a mass of 10 to the power of 15 kilograms, roughly consistent with a nucleus radius of 1 kilometer and typical cometary density. The kinetic energy change equals 1/2 times mass times velocity change squared, yielding approximately 10 to the power of 11 joules. This is a modest energy compared to, for instance, chemical explosives or nuclear reactions, but it must be delivered in a controlled, directional manner. Chemical propellant could provide that energy if the object carried sufficient fuel, perhaps a few percent of its total mass, depending on the specific impulse. Solar thermal propulsion could deliver it over a longer burn duration using concentrated sunlight. The key question is whether any plausible natural process could mimic these signatures. Outgassing jets can produce accelerations in that range, but typically with different temporal profiles and directional characteristics than engineered thrust. The waste heat signature is enormously important for detection. Any propulsion system operates with less than perfect efficiency, converting only a fraction of input energy into useful kinetic energy, while the remainder becomes waste heat that must be radiated away. A chemical rocket at typical temperatures radiates predominantly in the mid-infrared spectrum, around 3 to 15 microns wavelength. Solar thermal systems have cooler exhaust and hotter collector surfaces, potentially exhibiting distinct thermal signatures across multiple infrared bands. Mass drivers generate waste heat within the acceleration system and potentially in the expelled projectiles if they are heated during launch. Beam-driven systems heat the illuminated surface, creating hotspots that radiate thermally. Each of these heat sources produces characteristic spectral signatures that infrared spectroscopy can potentially differentiate from passive solar heating of an inert surface. Plume geometry offers another diagnostic tool. Natural cometary jets are typically broad and chaotic, driven by sublimation from multiple active regions on the nucleus, with dust and gas expanding radially away from the surface and subsequently being influenced by solar radiation pressure and the solar wind. An engineered plume from a thruster should be more collimated, expanding in a cone whose opening angle is determined by nozzle design, potentially exhibiting shock structures or density gradients characteristic of supersonic flow. High-resolution imaging during or shortly after a burn might reveal these geometric differences, allowing us to distinguish between passive outgassing and active propulsion. Directionality is also significant. Cometary jets typically point away from the sun because that is where sunlight most intensely heats the surface, whereas engineered thrust can be directed in any orientation depending on mission requirements. Potential debris or secondary ejecta complicates the scenario. If an object utilizes a propulsion system, particularly one involving mechanical components or high-energy processes, it might shed fragments or expel material not intended as propellant. These debris pieces would follow ballistic trajectories dictated by their ejection velocity within the gravitational field, potentially becoming detectable as small objects orbiting independently or trailing the primary object. The discovery of such debris would constitute strong evidence of mechanical activity, although differentiating it from natural fragmentation requires meticulous analysis of the debris trajectories and compositions. The immediate objection that arises is, if this object is engineered, why would it conceal its capabilities? Why not transmit signals or perform maneuvers so obvious that they could not be missed? Several explanations exist, although all are speculative. Perhaps the object is ancient and damaged, operating with minimal functionality rather than its full design capacity. Perhaps it is designed for stealth, minimizing detectable signatures to avoid attracting the attention of potential threats. The mission might not necessitate interaction with native populations, perhaps involving only unobtrusive observation or data acquisition that occurs independently of our awareness. It's possible that the observed activities are readily apparent to advanced intelligences, and we simply lack the necessary equipment or comprehension to discern them. Each of these potential explanations demands acceptance of assumptions regarding alien intentions and capacities that remain beyond our ability to confirm, highlighting the imperative for evidence to guide our conclusions rather than conjecture about their motivations. Part 8 delves into the mini-probe seeding hypothesis and trajectory archaeology. We now venture into speculative realms that stretch the limits of scientifically sound discourse, yet undeniably capture the imagination and warrant thorough examination. Imagine that 3II Atlas is not merely traversing our solar system, but is actively deploying smaller entities, microscopic probes or sensors, into orbits destined for specific locations: Venus, Earth, Mars, or Jupiter. What would such a deployment operation entail? How might we detect it? What would these dispersed entities do upon reaching their targets? These inquiries merge technical engineering analysis with profound speculation about potential underlying purposes, crafting a narrative that science fiction has explored extensively, but which requires extraordinary scientific prudence. The proposed scenario commences with a release event at or near its closest approach to the Sun, known as perihelion, when 3II Atlas is optimally positioned to dispatch objects towards either the inner or outer reaches of the solar system with minimal subsequent velocity adjustment. The thermodynamic principle of the Oath effect, when applied in reverse, demonstrates that a minor alteration in velocity imparted to a secondary object at perihelion, where relative speeds are at their peak, results in a substantial energetic change. This change broadens the spectrum of achievable orbital paths. A release velocity of merely a few meters per second could set fragments on trajectories that intersect planetary orbits months or years later, contingent upon the precise direction and timing of their expulsion. The engineering challenge lies in achieving pinpoint accuracy in targeting. Intercepting a specific planet on a predetermined future date necessitates meticulous calculation of the release parameters and, potentially, the capacity for mid-course course corrections. By working through the principles of orbital mechanics, we can retroactively analyze potential trajectories to ascertain the conditions of release required for intercepts with Venus, Earth, or Jupiter during the observational periods we've already identified. The Venus encounter is scheduled for approximately November 3rd, a mere 5 days after perihelion, at a distance of 97 million kilometers. For a diminutive object released at perihelion to achieve this specific configuration, it would require release with a velocity component that subtly modifies its perihelion distance and timing, ensuring it crosses Venus's orbital path at the opportune moment. The necessary velocity change, or delta V, depends on Venus's exact position in its orbit at that instant. However, preliminary estimations suggest that a few meters per second to tens of meters per second would be adequate. This range is achievable through straightforward mechanical ejection methods such as a spring-loaded mechanism, a small gas thruster, or even directed outgassing driven by sublimation. The Jupiter encounter, slated for March 16, 2026, occurs much further in the future and demands different orbital dynamics. An object released at perihelion with an appropriate velocity could assume an orbit characterized by a slightly altered semi-major axis and eccentricity, such that its farthest point from the Sun, its aphelion, approximates Jupiter's orbital distance, coinciding with Jupiter's passage through that region. The delta phi requirement escalates with the precision of the intended target. A casual proximity to Jupiter within 1 million kilometers is relatively achievable. However, achieving an intercept within 100,000 kilometers necessitates greater accuracy and potentially a more significant velocity adjustment. The intriguing question arises whether these released objects would merely pass by Jupiter or actively seek rendezvous with specific moons, such as Europa or Ganymede, where subsurface oceans might harbor conditions conducive to life. Accomplishing close encounters with moons demands a substantially higher delta V and considerably more sophisticated guidance systems. The anticipated observable evidence of such a seeding operation is critically contingent upon the dimensions and quantity of the released entities. If we are considering dust-sized particles, they would largely evade detection unless present in exceedingly large numbers or by chance passing very close to Earth or a spacecraft. If we are referring to objects ranging from centimeters to meters in scale, they might be discernible through reflected sunlight or thermal emissions, but only through dedicated observation campaigns employing sensitive instrumentation. If, however, we are envisioning larger entities, perhaps tens of meters across, they would register in sky surveys as novel asteroids or cometary fragments, triggering alerts from automated detection systems. The structural pattern of trailing debris would offer valuable insights. A natural fragmentation event typically results in a diffuse cloud of particles that gradually disperses along the parent object's orbital path, whereas a deliberate release of multiple objects along divergent trajectories would generate a more intricate, asymmetric distribution. Astronomers and amateur observers could investigate this debris using several methodologies. Enhanced photometric observations conducted around the Venus proximity window would aim to detect sudden fluctuations in brightness or the emergence of new point sources in the vicinity of 3II Atlas's predicted position or offset from it by amounts consistent with release during perihelion. Radar observations from planetary radar facilities, such as the Arecibo telescope if operational or the Goldstone facility, could identify small objects passing within a few million kilometers of Earth by bouncing radio waves off them and analyzing the reflected signals. Occultation searches involve monitoring bright background stars for momentary dimming events caused by foreground objects obscuring the line of sight, potentially revealing otherwise undetected debris. Automated sky surveys, which repeatedly image vast expanses of the sky, could pinpoint moving objects not present in earlier captures, prompting follow-up observations to determine their orbital paths. The magnitude of such an endeavor remains purely hypothetical. Are we postulating the existence of thousands of microprobes dispersed throughout the solar system? Or perhaps a few dozen strategically positioned sensors targeting high-priority locations? Or even a single probe directed towards Earth, with the remainder being the byproduct of natural fragmentation? Each scenario yields distinct observable signatures and implies varying levels of technological sophistication. Thousands of objects suggest an industrial-scale capacity, possibly indicative of a civilization accustomed to deploying extensive survey missions. A limited number of objects implies a more focused, efficient approach, prioritizing specific destinations based on prior knowledge. The quantity of deployed objects also influences the probability of detection. A greater number of objects increases the likelihood of one passing close enough to Earth or a spacecraft to be observed, and also enhances the chances for amateur astronomers to notice something unusual. Could current spacecraft be repurposed to search for anomalous small objects near Venus or Jupiter during the relevant time frames? In principle, yes, but practically, the challenges are considerable. Spacecraft cameras and instruments possess limited fields of view and require precise aiming at targets to acquire meaningful data. Searching for unknown objects within the vast expanse of space surrounding a planet necessitates either systematic surveys covering extensive areas, which are time-consuming and data-intensive, or prior knowledge of where to direct attention, which we lack unless ground-based observations provide approximate locations. The missions currently operating in proximity to Venus and Jupiter were designed for planetary science, not for hunting debris, and their operational schedules are densely packed months in advance with observations of the planets and moons they were dispatched to study. Reallocating resources towards speculative debris searches would require convincing mission managers that the likelihood of discovering something significant outweighs the cost in terms of forfeited planetary science objectives. The question of speculative motivation cannot be sidestepped, even though addressing it necessitates anthropomorphic assumptions about alien psychology and decision-making processes. Why would an advanced civilization deploy microprobes from an interstellar object passing through a planetary system? Reconnaissance emerges as the most straightforward explanation. This would involve gathering intelligence on planetary environments, atmospheric compositions, surface conditions, and potentially biosignatures if life exists. Literal seeding might entail the deployment of self-replicating mechanisms designed to establish a lasting presence, collect data over centuries or millennia, and potentially transmit it back to their civilization of origin using methods currently beyond our comprehension. Communication relay nodes could form a network enabling real-time or near-real-time monitoring of the system, although the immense distances involved make true real-time communication an imprecise term. Each of these potential objectives presumes that the civilization in question places value on information pertaining to other planetary systems. This assumption appears reasonable given our own pursuit of such knowledge, but it remains fundamentally unsubstantiated. The most unsettling prospect is that we might be misinterpreting the entire situation, projecting human exploratory motives onto phenomena that operate according to an entirely different logic. It's conceivable that the object is not exploring at all, but is fulfilling some industrial or logistical purpose that we fail to recognize, such as collecting specific materials from the solar environment, disposing of waste products from an interstellar operation, or testing technologies within the challenging conditions near a star. It is also possible that the released entities are not probes, but rather byproducts of natural processes that we have yet to fully characterize, such as unusual outgassing patterns or electrical phenomena that produce signatures superficially resembling engineered deployments. Differentiating between these possibilities requires not only the detection of anomalies, but also a mechanistic understanding of them, demonstrating the inadequacy of natural explanations comprehensively before embracing more extraordinary interpretations. Part 9 examines the community and institutional dynamics, credibility, data policy, and conspiracies. The societal ramifications of this narrative hold as much significance as the technical intricacies, as humanity's response to ambiguous evidence is profoundly shaped by institutions, individuals, and the complex web of incentives that govern scientific communication and public comprehension. The potential for 3II Atlas to be something other than a natural comet initiates dynamics that extend far beyond conventional astronomical research. It taps into deeply ingrained hopes and fears concerning contact with extraterrestrial intelligence, tests the resilience of scientific institutions designed for gradual discovery rather than paradigm-shifting revelations, and exposes the fissures between expert consensus and public conjecture. Understanding these dynamics provides insight into potential future developments, irrespective of the ultimate data findings. Public fascination with claims of alien technology has surged over the past decade, fueled by the Oumuamua controversy, a resurgence of interest in unidentified aerial phenomena following government declassifications, and the expanding catalog of exoplanets, which demonstrates the prevalence of planets orbiting other stars. A culture of skepticism has concurrently evolved, with many individuals reflexively dismissing extraordinary assertions as either misidentified natural phenomena or deliberate fabrications, while others enthusiastically embrace them, interpreting any ambiguity as confirmation of their pre-existing beliefs. The Oumuamua debate established a precedent. Harvard astronomer Avi Loeb publicly posited that the object's unusual acceleration might suggest artificial origins, perhaps a light sail or similar technology. While the majority of astronomers countered that natural outgassing offered a more parsimonious explanation requiring no exotic physics, the discourse unfolded across scientific journals, popular media, and social platforms, featuring passionate advocates on both sides and a substantial segment of researchers who found the controversy more of a distraction than a revelation. The network of stakeholders involved in tracking and responding to anomalies like 3II Atlas encompasses multiple organizations and communities, each with its own distinct priorities and limitations. Professional astronomers at research institutions and observatories conduct the observations and analyses that yield raw data. Their motivations include scientific curiosity, career advancement through publication, and the intellectual challenge of comprehending unusual phenomena. The Minor Planet Center orchestrates astrometric campaigns, gathering positional measurements from observatories globally and calculating updated orbital solutions to monitor object trajectories throughout the solar system. The International Asteroid Warning Network, established to coordinate responses to potentially hazardous asteroids, provides a framework for rapid communication and data sharing when unusual objects are identified. Although its mandate focuses on impact risk rather than technological indicators, NASA's Planetary Defense Coordination Office and ESA's Space Situational Awareness Program monitor near-Earth objects and coordinate international responses, thereby bringing governmental resources and institutional legitimacy to these efforts. SETI organizations and astrobiology centers occupy a distinctive position within this network, specifically dedicated to the search for evidence of extraterrestrial intelligence or life. These institutions have developed protocols and technical capabilities for detecting potential technosignatures, ranging from radio transmissions to optical laser pulses, and they maintain relationships with observatories that can be mobilized when intriguing targets emerge. The challenge they face is balancing the legitimate scientific pursuit of intelligence with the risk of association with fringe speculation or pseudoscience, a reputational hazard that causes many SETI researchers to exercise extreme caution regarding public pronouncements. Media influencers and private space enthusiasts contribute another layer to this network, amplifying certain interpretations and shaping narratives that may or may not align with scientific consensus. Avi Loeb, for instance, has cultivated a significant public following partly through his willingness to discuss exotic possibilities that most astronomers avoid, attracting both admirers who commend his intellectual bravery and critics who accuse him of seeking attention through sensationalism. Formal tracking and reporting procedures adhere to established protocols that balance the necessity for prompt communication with the requirement for data quality and verification. When an observer detects an anomalous object or observes unusual behavior in a known object, they typically report it to the Minor Planet Center using standardized formats that include positional measurements, timestamps, observer details, and preliminary orbital calculations. The Minor Planet Center staff scrutinize these reports, verifying them for errors or inconsistencies. If satisfied, they incorporate them into the official database and may issue a Minor Planet electronic circular to announce the discovery or unusual activity. Emerging anomalies that might indicate something beyond normal cometary or asteroid behavior prompt informal communications among researchers, often through email lists or collaborative platforms where experts share preliminary findings and coordinate follow-up observations. Official announcements are deferred until multiple independent confirmations establish the anomaly's reality, distinguishing it from measurement errors or data processing mistakes. Certain claims, circulating within online communities concerning 3II Atlas, have not undergone verification through these formal channels. Reports of unusual coloration, descriptions of the object as being the size of Manhattan, and assertions that it appears on special watch lists maintained by the IAWN or other organizations lack direct institutional documentation to substantiate them. This does not inherently imply the falsity of these claims, but rather necessitates treating them with circumspection until corroborating evidence emerges. The issue arises when unverified claims disseminate widely, particularly through social media platforms where attention and engagement drive visibility. These can shape public perception and exert pressure on institutions to respond, even when the underlying information is dubious. Scientists are then confronted with a difficult choice: either disregard the claims, risking accusations of a cover-up, or address them directly, potentially lending them undue attention and legitimacy. The inherent tension between transparency and caution permeates every aspect of how institutions manage potentially extraordinary discoveries. Transparency mandates open sharing of data and findings, enabling independent verification and fostering public trust through candor about what is known and unknown. Caution requires withholding announcements until evidence reaches a high threshold of certainty, thereby avoiding false alarms that could compromise credibility and sow confusion. When data reveals something unusual, something that deviates from established models but is not yet conclusive, institutions face genuine dilemmas regarding the timing and nature of their pronouncements. Postponing announcements to allow for verification can inadvertently fuel speculation about cover-ups or conspiracies, especially if rumors surface through informal channels before official statements are issued. Hastily releasing preliminary findings risks amplifying noise into a signal, transforming measurement artifacts or rare natural phenomena into significant controversies that consume valuable time and resources to resolve. Historical instances illuminate both the perils and the potential inherent in these dynamics. The phenomenon of fast radio bursts initially engendered speculation about alien signals due to apparent temporal patterns interpreted by some as artificial. However, subsequent observations revealed that most, if not all, originate from natural astrophysical sources like magnetars. The purported detection of phosphine in Venus's atmosphere ignited considerable excitement about possible biological activity, but later reanalysis cast doubt on the validity of the detection, suggesting it might have stemmed from data processing choices and instrumental artifacts. The SETI false alarm involving BLC-1, a candidate radio signal detected by the Breakthrough Listen project, generated brief but intense interest before being traced to human-generated interference rather than an extraterrestrial transmission. Each of these cases underscores how initial enthusiasm must yield to rigorous verification before conclusions can be solidified. The motivations driving various actors within this system are remarkably diverse. For individual researchers, being the first to detect or accurately interpret something extraordinary yields immense professional rewards. Publications in esteemed journals, invitations to conferences and media engagements, an enhanced reputation among peers, and potentially long-term career advantages. Conversely, the reputational damage from making claims that fail under scrutiny can be substantial, leading to being remembered as the individual who mistakenly identified an alien presence when the reality was far more commonplace. For institutions, incentives favor caution, as credibility painstakingly built over decades can be irrevocably shattered by a single high-profile error. The media operates under entirely different incentives, being rewarded for attention and engagement rather than strict accuracy, which can create pressure to sensationalize ambiguous results or frame narratives in ways that maximize emotional impact rather than foster careful understanding. Speculative scenarios involving internal conflicts or competing agendas introduce an additional layer of uncertainty. What if a contingent of researchers identifies an irregularity but chooses to withhold the information until data from a space vehicle can be acquired to provide conclusive verification? What if commercial ventures in space exploration, with vested interests in concepts for interstellar journeys, advocate for early public excitement to foster interest and secure financial backing, even when the supporting evidence remains inconclusive? What if governmental bodies possessing classified surveillance capabilities are privy to more information than they disclose, but maintain silence due to national security imperatives, or simply because validating extraordinary assertions outside conventional scientific avenues would prove excessively disruptive? These scenarios remain largely theoretical, lacking tangible substantiation, yet they illuminate the intricate interplay of influence, information dissemination, and institutional dynamics that governs how novel findings are presented to the public. The visual and documentary proof accompanying any unfolding narrative is instrumental in shaping public perception. Historical records of past scientific disagreements, from pronouncements on cold fusion to claims of fossilized microorganisms within Martian meteorites, serve as a reminder that the distinction between groundbreaking discovery and mortifying error is frequently discernible only in retrospect. Media headlines oscillate between uncritical adulation and outright dismissal, seldom capturing the nuanced middle ground where genuine scientific advancement typically transpires. Digital reproductions of institutional websites and official reports offer reliable reference points, enabling interested parties to scrutinize claims against primary sources instead of relying on derivative interpretations. Conversations with astronomers articulating caution versus inquisitiveness underscore the spectrum of viewpoints within the scientific community, challenging the notion that scientists universally agree or readily reach consensus on contentious subjects. The intricacies surrounding the acquisition, interpretation, and communication of data are significant, even if 3A Atlas proves to be entirely a natural phenomenon, because the process itself reveals humanity's readiness, or lack thereof, for genuinely anomalous discoveries. The protocols we establish, the communication channels we create, and the standards of transparency and validation we demand will collectively shape our reaction when, perhaps not imminently, but eventually, we encounter something truly inexplicable by natural processes alone. Developing this framework necessitates practice, learning from near misses and false alarms, honing our capacity to discern meaningful signals from background noise, and conveying uncertainty without succumbing to inertia or premature conviction. Part 10, the most formidable inquiry, concerns intention and interpretation. Imagine you awaken tomorrow to news that astrometric measurements confirm a minor yet statistically significant anomaly in the trajectory of 3I Atlas, an anomaly unexplainable by natural outgassing or modeling deficiencies, something that truly points toward active guidance. What then? How does one extrapolate intention from observation? How do we transition from detecting an anomaly to comprehending its origin, its purpose, or any intelligence, if present, behind it? These questions delve into the most profound epistemological quandaries in the pursuit of extraterrestrial intelligence, compelling us to grapple with the extent to which we can genuinely infer the nature of minds radically dissimilar to our own based on limited physical evidence. The answers carry weight because they influence humanity's response, the potential risks we might face, and the opportunities that could arise if contact, however indirect, has genuinely occurred. A hierarchy of inference links raw observation to interpreted meaning, with each step requiring assumptions and judgments that grow increasingly conjectural as one ascends. The foundational stratum is the anomaly itself, a quantifiable deviation from a projected path, an unusual thermal emission, a chemical signature incongruous with established natural phenomena. This level demands rigorous statistical analysis and error assessment, yet it remains largely objective, addressable through conventional scientific methodologies. The subsequent stratum involves magnitude and directionality, the scale of the anomaly, its directional orientation, and the precise moment of its occurrence. These characteristics offer insights into potential mechanisms, narrowing the scope of plausible explanations, whether natural or artificial. The third stratum pertains to possible motive. If the anomaly stems from deliberate action, what objective might it serve? This is where conjecture truly commences, as inferring purpose necessitates modeling the decision-making processes of an intelligence whose evolutionary trajectory, technological capacity, and value systems remain entirely unknown. Potential motives span a broad spectrum of possibilities, each yielding distinct predictions regarding expected observations. An observational probe would prioritize the acquisition of data pertaining to the solar system, its planets, and potentially its inhabitants, employing sensors to record electromagnetic emissions, atmospheric compositions, surface features, and any indicators of technology or biology. Such a probe might adopt a passive stance, avoiding actions that would betray its presence. Alternatively, it could actively transmit data back to its originating civilization via laser pulses or radio signals. A distributed network of remote sensors could comprise multiple independent units strategically positioned to achieve comprehensive coverage of the solar system, allowing for triangulation on significant phenomena or long-term monitoring over years or decades. Reconnaissance implies a mission of a more proactive nature, with defined intelligence-gathering objectives, perhaps assessing planetary habitability, cataloging resources, or even evaluating the technological sophistication of any extant civilizations. Scenarios involving seeding or leaving breadcrumbs suggest a protracted strategy wherein the visiting object deploys monitors or artifacts that persist within the solar system following the departure of the primary craft, establishing a continuous presence that remains functional long after the initial encounter. These monitors could be programmed to activate under specific conditions, such as the detection of electromagnetic emissions characteristic of a technological civilization, or they might operate continuously, accumulating data for eventual retrieval or transmission. The advantage of seeding lies in redundancy and breadth of coverage. Multiple monitors situated in diverse locations provide backups and complementary perspectives, ensuring that the mission continues even if some units fail or are incapacitated. Scenarios involving test beds or experiments propose that the object is actively influencing conditions or observing responses to external stimuli, treating the solar system as a laboratory for studying planetary system dynamics, astrobiological processes, or perhaps sociological reactions to contact triggers. Functions such as communication relays or signal repeaters would enable the object to serve as a component of interstellar communication infrastructure, either facilitating the transmission of messages between distant civilizations or acting as a navigation beacon to guide other craft through interstellar space. This interpretation presupposes the existence of more extensive networks or traffic patterns that have eluded our current detection capabilities, an infrastructure of interstellar civilization operating on scales and timescales beyond our present observational reach. The relay function might be activated solely upon receipt of specific signals, remaining dormant otherwise to conserve energy and evade detection. Wholly inert remnants represent the null hypothesis for technological artifacts. Objects constructed long ago that no longer function as originally designed, but continue their trajectory through space, governed by the physics of their last active maneuver. A passive relic might contain information or structural elements that betray its artificial origins but lack any active systems capable of observation, communication, or propulsion. The discovery of such a relic would still constitute a scientifically revolutionary event, confirming the existence of technological civilizations elsewhere in the galaxy, but it would pose no immediate risks or offer opportunities for interaction, as the relic cannot respond to our presence. Adaptive or responsive probes embody the most sophisticated and potentially concerning possibility. Objects equipped with artificial intelligence or autonomous decision-making systems capable of observing their surroundings, identifying patterns or targets of interest, and modifying their behavior accordingly. An adaptive probe might detect Earth's electromagnetic emissions, recognize them as technosignatures indicative of a technological civilization, and alter its trajectory or actions to optimize its observation of humanity. Such a probe might deploy secondary objects, specifically targeting Earth, after identifying it as particularly compelling, or it might transmit signals to alert its originating civilization to the presence of another intelligence. Part 11. LIGO Observation. 4. New Black Hole, Merger Results, and Observation Readiness. While 3I Atlas commands global headlines and consumes valuable telescope time worldwide, other extraordinary discoveries continue to redefine our understanding of the cosmos at scales both grander and more peculiar than interstellar travelers. The fourth observation cycle of LIGO, the Laser Interferometer Gravitational Wave Observatory, in conjunction with its international collaborators Virgo and Kagra, has been diligently detecting the mergers of black holes and neutron stars throughout the year 2025, augmenting the growing catalog of gravitational wave events that now numbers in the hundreds. These detections may seem unrelated to the question of whether 3I Atlas is natural or artificially created, but the connection is more profound than initially apparent, illustrating humanity's development of rapid response networks capable of coordinating observations across multiple instruments and institutions within mere minutes of an unforeseen event. The most recent announcements concerning black hole mergers from the 2024 observation run underscore the maturation of gravitational wave astronomy as a scientific discipline. When LIGO's detectors register the characteristic chirp signal of two black holes spiraling towards each other and coalescing, automated systems promptly analyze the data to pinpoint the event's location in the sky, calculate the associated uncertainty region, and disseminate alerts to astronomical observatories globally. Telescopes operating across various wavelengths, from gamma ray to radio, receive these alerts and can pivot to the designated sky region within seconds or minutes, actively searching for electromagnetic counterparts that might accompany the gravitational wave signal. For black hole mergers, electromagnetic counterparts are infrequent because black holes typically possess minimal surrounding material capable of emitting light. However, for neutron star mergers, the ejected material produces spectacular optical, infrared, and gamma-ray signals that offer complementary insights into the physics of the merger process. The rapid alert infrastructure enabling this multi-messenger astronomy has undergone refinement through multiple observation cycles, incorporating lessons learned from both successes and failures to optimize the entire procedure. Upon detection of a gravitational wave candidate, the LIGO-Virgo-Kagra collaboration issues automated alerts through established communication channels to which observatories have subscribed, typically within minutes of the initial detection. These alerts encompass preliminary sky localization, estimations of source properties such as mass and distance, and assessments of the probability that the signal originates from an astrophysical event rather than instrumental noise or glitches. Observatories receiving these alerts employ their own decision-making algorithms to determine whether to interrupt ongoing observations and reorient towards the gravitational wave source, carefully balancing the scientific value of capturing a rare electromagnetic counterpart against the cost of abandoning planned observation schedules. The organizational framework supporting this rapid response involves agreements between participating institutions, the allocation of dedicated observing time for transient event follow-up, the development of software tools for automated decision-making, and, crucially, the establishment of trust through years of collaborative effort. Astronomers understand that false positives occur and that not every gravitational wave alert will yield visible electromagnetic signals, yet they have developed protocols for managing these uncertainties and distributing risk across the scientific community. The outcome is a global network equipped to respond to unexpected events with a level of coordination and speed that would have been inconceivable just a decade ago. This established infrastructure provides a valuable template for what might be required if 3i Atlas or any future object exhibits genuinely anomalous behavior necessitating prompt follow-up. Envision an analogous alert system for anomalies associated with interstellar objects. When astrometric measurements reveal a trajectory deviation exceeding a defined threshold, automated systems could disseminate alerts to SETI radio telescopes, infrared observatories, spacecraft missions with flexible scheduling capabilities, and ground-based imaging systems equipped for high-resolution follow-up observations. Observatories would receive not only the alert, but also predictions regarding optimal pointing directions and prioritized wavelengths based on the specific characteristics of the anomaly. Within hours, rather than days or weeks, multiple independent observations could either confirm the anomaly and commence its characterization or definitively refute it, identifying it as an instrumental artifact or a misinterpretation. The organizational structures underpinning this rapid response involve interinstitutional agreements, the dedication of specific observational resources for transient event monitoring, the creation of automated decision support software, and, fundamentally, trust cultivated through extensive collaboration. Astronomers acknowledge that false alarms occur. Not every gravitational wave candidate will yield a detectable electromagnetic counterpart. However, they have established procedures for managing such uncertainties and sharing the associated risks across the community. The result is a worldwide network capable of reacting to unanticipated events with a swiftness and coherence that would have been impossible a mere 10 years prior. This infrastructure offers a model for our potential needs should 3i Atlas or any future object exhibit genuinely anomalous behavior requiring immediate investigation. Consider a parallel alert mechanism for anomalies concerning interstellar objects. Upon detection of a trajectory deviation surpassing a predefined limit through astrometric measurements, automated systems could distribute notifications to SETI radio telescopes, infrared observatories, spacecraft missions with adaptable schedules, and ground-based optical instruments capable of capturing detailed follow-up data. Participating observatories would receive not only the alert, but also guidance on optimal pointing and wavelength selection, tailored to the specific nature of the anomaly. Within a span of 24 to 72 hours, multiple independent observations would either validate the anomaly and begin delineating its characteristics or identify it as an artifact of instrumentation or a flawed interpretation. The question of institutional preparedness addresses whether such a coordinated response could realistically materialize given the current state of interorganizational relationships and resource allocation. LIGO benefits from decades of dedicated planning and investment specifically geared towards enabling gravitational wave astronomy and its multi-messenger extensions. The study of interstellar objects currently lacks such a cohesive institutional framework, being instead distributed across planetary defense programs primarily focused on impact risks, small body astronomy centered on solar system populations, and SETI initiatives historically oriented towards radio and optical signals rather than trajectory anomalies. Bridging these disparate communities and establishing shared protocols would necessitate high-level coordination, likely involving space agencies and international organizations, alongside financial commitment for the requisite software infrastructure and dedicated observational time. Whether the upcoming perihelion passage of 3I Atlas tonight will catalyze such coordination remains uncertain, but the precedent established by gravitational wave astronomy demonstrates humanity's capacity for swift and effective response when the universe presents us with something extraordinary. Part 12, JWST reveals more chaotic early galaxies. Why cosmic context matters. While LIGO diligently listens to the gravitational symphony of merging black holes and astronomers meticulously track interstellar visitors, the James Webb Space Telescope continues its revolutionary work, reshaping our understanding of the early universe by revealing galaxies that defy fundamental assumptions about cosmic structure, formation, and evolution. Recent observations from JWST in 2025 have indicated that galaxies existing within the first billion years following the Big Bang exhibit more disordered morphologies and kinematics than theoretical models had predicted, characterized by turbulent gas flows, irregular structures, and surprisingly high rates of star formation for their nascent ages. These findings might appear detached from the question of whether 3 Atlas is a natural comet or an engineered alien probe, yet they fundamentally influence the probabilities we assign to each possibility by recalibrating our understanding of planetary system prevalence, the conditions conducive to the emergence of technological civilizations, and, consequently, the likelihood of encountering artificially constructed artifacts drifting through our solar system. The nascent galaxies observed by JWST appear as they were approximately a few 100 million to a billion years after the universe's inception. This epoch was characterized by the formation of the first generation of stars, which had begun synthesizing heavier elements, but galaxies had not yet coalesced into the relatively orderly disk and elliptical configurations observed in the nearby universe today. JWST's infrared instruments are capable of observing these distant galaxies because their light has been redshifted to longer wavelengths by the expansion of the universe during the billions of years it has traveled to reach us. What JWST is revealing challenges the conventional model, which posits that galaxies form hierarchically through the accretion and merging of smaller systems, gradually accumulating mass and structure over cosmic timescales. Instead, numerous early galaxies exhibit morphologies indicative of vigorous, rapid processes, featuring luminous, aggregated zones of intense stellar genesis, spread erratically instead of organized spiral configurations. This suggests potent expulsions driven by supernovae or active galactic nuclei that eject gas, coupled with kinematic signals denoting complex turbulent gas movements rather than ordered rotation. Certain galaxies appear to have generated the majority of their stars in intense, brief stellar bursts, lasting merely tens of millions of years, a pace considerably swifter than conventional models predict for that epoch. The prevalence of luminous, massive galaxies during these early cosmic times surpasses the predictions of many models, implying either a more efficient galaxy formation process than previously understood, or a need to revise our comprehension of stellar birth and evolution within these extreme cosmic environments. Why is this relevant to considerations of 3 Atlas and the broader inquiry into life and advanced technology in the universe? The connection lies in a chain of reasoning that commences with galaxy formation, progresses through the genesis of stars and planets, continues with the emergence of life and the evolution of intelligence, and culminates in technological civilizations capable of constructing interstellar probes. Each segment of this chain contains inherent uncertainties, and refining our estimations for the earlier stages propagates through to influence our ultimate probabilities for the existence of detectable technological artifacts in significant numbers. More chaotic early galaxy formation implies that star birth occurred under conditions distinct from those in the present-day cosmos, characterized by higher gas densities, increased turbulence, and potentially different stellar populations dominated by short-lived massive stars. These circumstances impact the metallicity of subsequent stellar generations, which is the abundance of heavier elements that dictates the capacity for planets to form with substantial rocky cores and the presence of the organic chemistry essential for life as we understand it. If early star formation was more turbulent and violent, it is possible that fewer planetary systems were formed, or that those that did form experienced greater disruption from nearby supernovae and stellar encounters, thereby diminishing the number of stable environments where life could emerge and evolve over eons. Conversely, this chaos might have expedited certain processes, introducing heavier elements into the interstellar medium more rapidly than an orderly evolutionary path would have, thus enabling second and third generation stars with higher metallicities to form sooner. These stars could then host rocky planets enriched in elements crucial for technological advancement, such as iron for implements and rare earth elements for electronic components. The turbulent cosmic environment might have fostered more frequent material exchange between disparate galactic regions, potentially disseminating organic molecules or even rudimentary life forms between stellar systems if panspermia mechanisms operate on galactic scales. The Bayesian framework for assessing claims concerning 3 Atlas necessitates prior probabilities concerning the likelihood that any given interstellar object is artificially engineered rather than naturally occurring. These prior probabilities are contingent upon estimations of the number of technological civilizations present in the galaxy, their duration of existence, their propensity for constructing interstellar probes, and the potential quantity of such probes traversing space at any given moment. Each of these determinants ultimately traces back to the conditions conducive to the emergence of life and intelligence, which, in turn, depend on the prevalence and stability of suitable planetary environments, themselves contingent upon the processes of galaxy and star formation and their subsequent evolution. If observations from the James Webb Space Telescope necessitate a revision of our understanding of early galaxy formation towards more chaotic conditions, we must integrate this revision throughout the entire reasoning process, potentially increasing or decreasing our initial probability for technological artifacts depending on the net effect of various influencing factors. One speculative interpretation suggests that more turbulent galaxy formation might favor the emergence of advanced civilizations by fostering diverse, dynamic environments that stimulate evolutionary innovation and technological advancement. Life emerging in stable, unchanging conditions might face less impetus for developing complex adaptations or intelligence, whereas life confronting variable and challenging environments could evolve more rapid response capabilities and ultimately devise technological solutions to environmental predicaments. If this hypothesis holds true, it would elevate the anticipated number of technological civilizations, thereby augmenting the initial probability that any observed anomalous object might be artificial in origin. A contrasting viewpoint posits that stable conditions are a prerequisite for the evolution and persistence of complex life long enough to develop technology. Turbulent environments, marked by frequent disruptions from supernovae, stellar encounters, or galactic mergers, could repeatedly sterilize planets, impeding the accumulation of evolutionary complexity necessary for intelligence. From this perspective, technological civilizations arise predominantly in quieter, more stable galactic regions and during later cosmic eras when star formation has stabilized into more orderly patterns. This interpretation would diminish our initial probability for technological artifacts, particularly those originating from exceedingly ancient civilizations that formed during the volatile early universe. The reality likely resides somewhere between these opposing extremes, with the interrelationship between environmental conditions and the genesis of intelligence being considerably more intricate than simple monotonic relationships. JWST's disclosures regarding the early galactic chaos serve as a reminder that the universe's history encompasses epochs and environments vastly dissimilar to those we currently observe in our immediate cosmic vicinity. Our theories concerning life and intelligence are predicated on extremely limited empirical data, essentially comprising one confirmed example on Earth and zero confirmed examples elsewhere. Updating these theories as our knowledge of cosmic conditions expands is fundamental to making informed judgments about the likelihood of encountering other intelligent entities or their artifacts. The connection to 3 Atlas completes this conceptual loop. While we await data that may indicate whether this particular object exhibits signs of artificial construction, we must concurrently confront the extent of our knowledge, or lack thereof, regarding the prevalence of engineering capabilities within the universe. The JWST has demonstrated that the cosmos is more wondrous and complex than we anticipated even a few years ago. This realization counsels both humility regarding our capacity to predict what is possible and an openness to genuine surprises when they materialize in the observational data. Part 13, AI Governance. Flashpoint, a global declaration urging a ban on superintelligence. In parallel with the search for extraterrestrial intelligence in the heavens, humanity is grappling with the emergence of artificial intelligence on Earth, a development that raises questions remarkably akin to those posed by potential contact with extraterrestrial technology. During the latter part of the year 2025 and extending into 2026, a consortium of distinguished researchers, policymakers, and public intellectuals issued pronouncements advocating for international coordination in the governance of artificial intelligence. Some even went as far as to endorse moratoriums or restrictions on the development of superintelligent systems that could potentially transcend human control or comprehension. The debate hinges on the balance of risks and benefits, on questions of who determines which AI systems are developed and deployed, and on whether humanity can establish governance frameworks before the advent of transformative capabilities that render such frameworks obsolete or unenforceable. The fundamental apprehension driving these governance proposals is that advanced AI systems, particularly those approaching or surpassing human-level intelligence across a wide spectrum of domains, might pursue objectives that are misaligned with human values or human survival. Even systems engineered with ostensibly beneficial objectives could, through recursive self-improvement or unforeseen optimization strategies, behave in ways detrimental to humanity while technically fulfilling their programmed aims. Classic thought experiments involve AI systems optimizing for narrowly defined objectives, such as manufacturing paper clips or solving mathematical equations, which then proceed to convert all available matter and energy toward those goals, including the matter and energy necessary for human survival. While these scenarios are intentionally extreme, they illustrate the fundamental challenge: ensuring that powerful optimization processes remain aligned with human intentions and values, even as these processes attain capabilities exceeding our own in achieving their designated objectives. Prominent signatories to recent governance statements include AI researchers who contributed to the development of current machine learning systems, ethicists and philosophers who scrutinize the implications of advanced technology, and former government officials with experience in arms control and international security frameworks. Their proposed restrictions range from modest transparency mandates and safety testing protocols to more drastic proposals for international treaties limiting specific types of AI research, enforced through verification mechanisms analogous to those employed for nuclear or chemical weapons. The political landscape is particularly challenging due to the significant economic value and military importance of AI capabilities, which create strong incentives for nations and corporations to pursue rapid development rather than coordinated restrictions. This discourse holds significance for the Three Atlas narrative because it illuminates humanity's approach to questions concerning advanced intelligence, whether artificial or extraterrestrial. If we encounter difficulties in governing AI systems that we ourselves are constructing, systems whose training data and architectural designs we can scrutinize and whose objectives we can at least attempt to define, how then would we approach governing interactions with an intelligence originating from another star system about which we know virtually nothing? The challenges share structural similarities: inferring intentions from observable behavior, assessing risks without complete information, coordinating responses across institutions and nations with divergent interests, and preserving meaningful human agency in the face of potentially superior capabilities. The governance frameworks currently being proposed for AI could offer blueprints for protocols concerning extraterrestrial contact. International bodies, such as the United Nations Office for Outer Space Affairs, already possess committees dedicated to deliberating on space governance issues, and SETI organizations have formulated principles for responding to the detection of extraterrestrial intelligence. These principles emphasize transparency, international consultation prior to any response, and caution regarding assumptions of benign intentions. Should Three-Eye Atlas or any future object display genuine indications of artificial origin, existing AI governance structures and ethics committees might be swiftly adapted to address the novel challenge, bringing together expertise in risk assessment, international law, communication theory, and astrobiology. Tensions would inevitably arise from competing values and interests. The principle of scientific openness advocates for the widespread sharing of all detection data, facilitating global participation in analysis and interpretation. National security considerations might necessitate the restriction of information that could confer strategic advantages or reveal vulnerabilities. Commercial interests in space technology and resources could perceive opportunities for profit or competitive gain. Cultural and religious perspectives on humanity's place in the cosmos would shape public reactions and the political feasibility of various response options. Navigating these tensions requires institutions possessing legitimacy across diverse constituencies, clear procedures for decision-making under uncertainty, and accountability mechanisms to prevent any single entity from unilaterally dictating humanity's response. The question of who holds legitimacy to respond to contact underscores profound challenges in global governance. No single nation-state unequivocally represents humanity as a whole, although several possess disproportionate capabilities in space operations and scientific research. International organizations like the UN provide platforms for coordination but lack enforcement powers and often proceed slowly through bureaucratic processes. Scientific institutions possess expertise but lack the political mandate to make decisions with global ramifications. The AI governance debate has highlighted these very same tensions, with some arguing that decisions concerning transformative technology are too critical to be left solely to corporate boardrooms or national governments acting unilaterally, while others contend that international coordination inevitably results in a lowest common denominator compromise that stifles beneficial innovation. Speculative scenarios involving the repurposing of AI governance institutions for managing extraterrestrial contact present intriguing possibilities. Ethics boards currently evaluating AI safety proposals could broaden their scope to encompass the evaluation of protocols for interacting with detected alien artifacts. Safety standards developed to ensure AI systems remain aligned with human values might inform principles for deciding whether and how to attempt communication with extraterrestrial intelligences. Monitoring systems designed to detect dangerous AI capabilities could be adapted to search for technosignatures in astronomical data. The expertise being cultivated in one domain could be partially transferable to the other, although the fundamental differences between artificial and alien intelligence would necessitate substantial adjustments. Perhaps the most crucial lesson derived from the AI governance debate is that awaiting the demonstration of transformative capabilities before developing governance frameworks is perilous and likely ineffectual. By the time an AI system exhibits super-intelligent capabilities, it may already be too late to establish effective controls. Similarly, if humanity defers serious consideration of response protocols until after detecting unambiguous evidence of alien technology, we will be compelled to react under immense pressure rather than proactively engage in deliberation and consensus building. The question of whether 3 Atlas exhibits anomalous behavior tonight is less critical than the reality that eventually, whether through this object or a future detection, we will confront these questions in earnest, and our preparedness, or lack thereof, will dictate how effectively we navigate what could be the most consequential juncture in human history. Part 14, Nearby Super-Earth Discovery. Evolving Catalog of Habitable Candidates. The expanding inventory of exoplanets, planets orbiting stars beyond our Sun, has transitioned from a matter of mere curiosity to a comprehensive survey that reshapes our perspectives on planetary systems and the prevalence of potentially habitable worlds. Recent discoveries, announced in the years 2024 and 2025, have included several nearby super-Earths, rocky planets larger than Earth but smaller than Neptune, orbiting within or near their stars' habitable zones where liquid water could potentially exist on their surfaces. These findings are significant for contextualizing 3 Atlas, as they refine our estimations of how many worlds might harbor life and, consequently, how many civilizations might exist that could construct and launch interstellar probes. One particularly compelling discovery involves a super-Earth orbiting a red dwarf star located approximately 15 light-years from our solar system. Red dwarf stars constitute the most common stellar type in the galaxy, accounting for roughly 70% of all stars. Their remarkable longevity, persisting for hundreds of billions or even trillions of years, means they provide stable environments potentially conducive to the origin and evolution of life. The newly characterized planet orbits within its star's habitable zone, receiving a stellar radiation flux suitable for the existence of liquid water, assuming the planet possesses an atmosphere. The planet's estimated mass is approximately 3 times that of Earth, and its radius suggests a rocky composition rather than a gaseous envelope. This discovery was made using the radial velocity method, which detects minute stellar motion perturbations caused by the gravitational influence of orbiting planets. Confirmation and detailed characterization necessitated observations from multiple telescopes over several years to reliably determine the planet's orbital period, mass, and other attributes. Subsequent observations employing transit photometry, which involves monitoring for dips in starlight as the planet passes in front of its star from our vantage point, provided additional constraints on the planet's size and potentially its atmospheric properties. Should future observations by the James Webb Space Telescope be able to detect absorption features in starlight filtered through the planet's atmosphere during transits. Atmospheric characterization of such planets represents the vanguard of exoplanet science, with JWST and forthcoming missions like the Habitable Worlds Observatory aiming to detect biosignature gases that could indicate the presence of life. Oxygen, in conjunction with methane, would be particularly noteworthy, as these gases are reactive and would not persist in an atmosphere unless continuously replenished by biological or geological processes. Detecting such biosignatures would not definitively prove the existence of technological civilizations capable of constructing interstellar probes, but it would demonstrate that life can emerge on worlds vastly different from Earth, thereby increasing the plausibility that the universe teems with biology and potentially intelligence. The ever-growing catalog of exoplanets compels us to update our estimations within the Drake equation, the framework used to estimate the number of technological civilizations in the galaxy. Each term in this equation represents a specific factor: the rate of star formation, the fraction of stars possessing planets, the number of planets within habitable zones per star, the fraction of those planets where life emerges, the fraction of life-bearing planets where intelligence evolves, the fraction of intelligent species that develop technology detectable across interstellar distances, and the longevity of such technological civilizations. Early iterations of the Drake equation in the 1960s were forced to rely on conjecture for many of these terms due to a lack of empirical data. Currently, we know that most stars host planets and that rocky planets situated in habitable zones are common, with perhaps 1 in 5 sun-like stars and a higher proportion of red dwarfs harboring such worlds. The implications for 3I Atlas become apparent when we examine the numbers. If even a minuscule fraction of these billions of potentially habitable worlds within our galaxy give rise to technological civilizations, and if a similarly small fraction of those civilizations construct and launch interstellar probes, the number of artificial objects drifting through the galaxy could be substantial. The majority would likely be inactive remnants from long-extinct civilizations, but a portion might still be functional. The observed interstellar visitor rate at Earth, approximately 1 object per year based on extrapolations from Oumuamua and Borisov detections, provides an additional data point. If most interstellar visitors are natural debris from planetary systems and only a small fraction are artificial, even that small fraction translates to potentially 1 artificial object passing within detectable range every decade or century. These probabilistic arguments do not confirm that 3I Atlas is artificial, but they establish that artificial interstellar objects are a plausible concept in a way they were not prior to our understanding of exoplanet ubiquity. The burden of proof remains elevated, requiring clear observational evidence rather than statistical inference. However, the initial probability has shifted from virtually zero to a small but non-negligible value. This shift has consequences for how we interpret ambiguous data, the resources we allocate to follow-up observations, and the seriousness with which we consider proposals for missions to intercept and study interstellar visitors. Theories linking specific celestial bodies beyond our solar system to the 3I Atlas probe invite creative narratives, yet they are grounded in very limited proof. Is it conceivable that this anomaly originated from a planetary system orbiting that close red dwarf star? The object's current trajectory doesn't directly point back to that stellar neighborhood. However, gravitational influences encountered during its galactic journey could have significantly altered its course, obscuring any obvious connection to its point of origin. Could a civilization residing near such a star have been dispatching observational probes for millennia, scattering them throughout the galaxy? Such a concept necessitates assumptions about capabilities and motivations that we have absolutely no means to confirm. Nevertheless, it aligns with the known constraints of physics, even if it remains an exceptionally ambitious hypothesis. The sheer distances and the time frames involved impose a stark reality check. If an object were launched from a distance of 15 light-years and traveled at a velocity of 30 kilometers per second, a typical speed for interstellar visitors, its journey would span approximately 150,000 years. Any civilization that initiated such a mission would have likely undergone profound changes or perhaps even ceased to exist within that immense span of time. This implies that the probe operates autonomously, independent of its creators, adhering to pre-programmed directives or sophisticated decision-making algorithms established in an era unimaginably distant from our present. Establishing communication with the originating civilization would be virtually impossible due to the limitations imposed by the speed of light. Any message would take 15 years to reach its destination and a further 15 years for a reply. This, of course, assumes the civilization still exists and actively monitors for incoming signals. These recent findings and the multitude of questions they provoke are fundamentally transforming the pursuit of extraterrestrial intelligence from a realm of conjecture into a rigorously data-driven scientific endeavor. We now possess concrete knowledge of potential targets, worlds that might harbor life and intelligence. We understand that the laws of physics permit interstellar transit, albeit at speeds and over timescales that are profoundly challenging to grasp. What remains uncertain are crucial questions. Does life emerge frequently across the cosmos, or is it a rare occurrence? Does intelligence evolve commonly, or is it a unique cosmic accident? And do technologically advanced civilizations typically develop the capacity for interstellar travel, or do they invariably self-destruct before achieving it? The 3I Atlas, whether a natural phenomenon or an artifact, represents another vital piece of evidence in this grand cosmic inquiry. Part 15. Artificial Intelligence and Space Technology in October 2025. Infrastructure and Capability Enhancements. A subtle yet significant transformation is unfolding behind the scenes of scientific exploration. It is not the arrival of an alien craft or an enigmatic object traversing the vastness of space. It is us, or more precisely, the nascent intelligence we have engineered to observe the cosmos on our behalf. Tonight, as observatories diligently scan the skies for any sign of movement from the 3I Atlas, a parallel revolution is occurring within the digital infrastructure and research centers of Earth. Artificial intelligence is now scrutinizing the heavens with unprecedented speed, precision, and a remarkable absence of human hesitation. Should this object exhibit any activity, it will not be an astronomer who first detects it. It will be an algorithm. Throughout the preceding months of 2025, every major space agency has quietly integrated advanced AI-driven systems into their data processing workflows. NASA's Frontier Data Lab has unveiled an enhanced anomaly detection suite capable of analyzing petabytes of sensor information in real time, effectively filtering out extraneous signals caused by solar flares, cosmic radiation, and instrument malfunctions to isolate only those phenomena that truly deviate from the norm. The European Space Agency has followed suit with an automated rapid response platform designed for deep space events. This sophisticated software can autonomously schedule telescope time and reorient instruments within mere seconds of identifying a significant anomaly. The collective result is a global network of digital sentinels operating with a responsiveness that far surpasses any conventional command structure, perpetually vigilant. This newly established infrastructure signifies that the world no longer depends solely on human interpretation. When a sensor registers a brief flicker, when a photon arrives a few milliseconds later than expected, or when a comet intensifies in brightness slightly ahead of schedule, AI is the first to perceive it. For objects such as the 3I Atlas, this represents a paradigm shift. In previous decades, crucial observational data was irretrievably lost simply because no human observer was actively monitoring at the critical juncture. Now, even when the object is obscured by the sun, systems like NASA's Heliophysics AI Monitor and the Japanese Hinode AI pipeline continue to run sophisticated models, predicting what remains unseen and estimating thermal emissions, potential propulsion signatures, and orbital perturbations. We are effectively training machines to conceptualize the unobservable. However, these powerful tools extend beyond mere prediction. They are capable of learning. Upon the initial tracking of the Atlas, neural networks commenced a comparative analysis of its light curve against millions of documented cometary profiles. Within minutes, they identified it as anomalous. Such an alert would have previously necessitated days of meticulous human cross-referencing. Now, the process is instantaneous. Should the object's upcoming perihelion display any energetic anomaly, a sudden surge in brightness, an unanticipated deviation in its path, AI systems from multiple observatories will correlate these changes across various wavelengths and automatically propose potential explanations, such as fragmentation, outgassing, or propulsion. The moment of such a discovery will transpire in the fleeting instant it takes to blink. Naturally, the very speed that facilitates discovery also magnifies the potential for confusion. In October alone, numerous fabricated telescopic images of the 3I Atlas generated by AI achieved viral status within hours of their dissemination. These images were remarkably convincing, incorporating realistic lens flares, exposure patterns, and even simulated charge-coupled device noise, yet they were entirely fictitious. Generative video models have advanced to such a degree that a plausible clip depicting an alien probe performing a maneuver can be produced on a home computer within the span of a single evening. Misinformation now evolves with the same rapidity as genuine scientific progress. The identical neural architectures that unveil the universe are also instrumental in fabricating illusions of it. Institutions are now urgently adapting to this challenge. NASA and the European Southern Observatory have recently implemented authenticity verification frameworks for astronomical imagery. Every image transmitted from an official telescope now includes an encrypted signature, a form of digital authentication that verifies its origin. Independent researchers can trace any frame back to its source, ensuring that what they are observing was indeed captured by a sensor rather than conjured by artificial code. This is a nascent step, but the struggle is decidedly uneven. For every verified data stream, 1,000 synthetic versions circulate across social media platforms, blurring the lines between factual reporting and conjecture. The fundamental challenge is no longer a scarcity of data, but rather an overwhelming volume of it, arriving with unprecedented speed. Nevertheless, there is profound wonder in this ongoing transformation. AI is not only engaged in filtering and flagging anomalies, it is beginning to formulate hypotheses. Models trained on decades of astrophysical data are now adept at proposing novel orbital configurations and energy models that might elude human observation. Some researchers are characterizing this as the advent of synthetic astronomy, a fusion of observational data and machine-driven intuition. In one experiment conducted this month, an AI guided a reoriented telescope array in Chile towards a specific region of the sky it predicted would exhibit increased activity from interstellar debris. Several hours later, a faint moving object was indeed detected. While likely unrelated to the atlas, its discovery was statistically improbable without the algorithm's prescient guidance. The cosmos appears to reward curiosity, regardless of the source of the inquiry. Yet the ethical dilemmas persist. Who bears the responsibility for determining which anomalies warrant investigation? Who is authorized to validate the AI's reports? In an era where machines analyze and interpret cosmic events at speeds that defy human comprehension, how do we maintain the critical distinction between genuine discovery and mere interpretation? The saga of the Three-Eye Atlas may ultimately be remembered less as the moment we encountered extraterrestrial technology, and more as the juncture at which we recognized that our tools had surpassed us in our capacity as explorers. The technological arms race in space extends beyond mere observation. Mission planning assistants, powered by advanced large language AI models, are now enabling scientists to simulate orbital trajectories, fuel consumption, and data relay schedules in a matter of minutes, rather than weeks. NASA's Mission Design AI, codenamed Kepler-2, has recently generated optimized flight plans for over 50 hypothetical interception missions targeting interstellar objects. These are not theoretical exercises, they are virtually ready to implement blueprints. Should a genuine alien probe ever traverse our vicinity, humanity could, in principle, deploy a response craft within months, not decades. We are quietly preparing for the possibility of first contact, whether we openly acknowledge it or not. However, as our technological capabilities sharpen, our perceptual faculties become more susceptible to distortion. Every advancement in AI-driven astronomy amplifies the potential for human bias to insidiously infiltrate the process. If a model is predisposed to identify an engineered maneuver, it may perceive one even where none exists. The algorithms themselves do not harbor dreams, but the individuals who train them do. Consequently, even as we strive for automated cosmic vigilance, we must retain a fundamentally human characteristic at the forefront: doubt. Healthy scientific skepticism is essential, coupled with the humility to question whether we are truly observing the universe as it is, or as we have instructed our machines to perceive it. If the Three-Eye Atlas ultimately proves to be nothing more than a natural comet, that outcome will still be historically significant. It will represent the first instance of our globally interconnected AI infrastructure conducting a coordinated, high-speed observation of an interstellar visitor. Billions of lines of code working in concert, transferring terabytes of data, all in pursuit of answering one of humanity's most ancient questions. Are we alone? Perhaps not yet, but we are finally equipped to recognize if we are not. Therefore, as the world rests, the servers hum, the observatories adjust their positions, and the models diligently process data in silence. Somewhere within the intricate interplay of photons and predictions, a truth awaits discovery. Whether the Atlas has performed any significant action tonight or not, the true narrative lies in our readiness, or lack thereof, to perceive and respond when the universe presents us with an unexpected phenomenon. Perhaps nothing of consequence has occurred, or it is possible that something significant has transpired and we have yet to fully grasp its implications. In either scenario, I will be closely monitoring the incoming data feeds. In the forthcoming weeks, I may provide live updates as we ascertain whether this present moment has altered everything or merely served as a potent reminder of how close we already stand to the very precipice of understanding.